Yeah, today I'm going to talk to you about the Kibble Balance, some more specifics, and how we realize the kilogram from fundamental constants. And so you've heard a little bit about Planck's constant, but we'll go into the other fundamental constants that we need in order to do the realization. So while the kilogram is tied to 1, we need other constants in order to actually perform the realization. So I also want to thank my colleagues Barry Wood and Carlos Sanchez and Jacques Liard and Nathan Murnahan, who've done a lot of work and on the Kibble balance, gravity, and the electrical measurements. So just to start, everybody knows the famous equation by Einstein came about around 1905, for which he won the Nobel Prize. Came around 1905, and that shows that the energy of a particle is related to mass through the speed of light squared. And so, and if we combine that with work from Max Planck that happened just a little bit earlier, we know that the energy of a photon is equivalent to, can be converted to, is equivalent to frequency times Planck's constant. So there's a constant of proportionality between energy and frequency, and a constant of proportionality between mass and a frequency as well when you combine these two equations. So the difficulty is measuring. So if we can fix H and we can fix C, which are fixed now in the new definition, in order to do that, we need to be able to measure those values to very, very high precision or accuracy, and that took quite a bit of time. Particularly took a few concepts that won Nobel Prizes. And so we'll talk about the Kibble balance, which was originally conceived by Brian Kibble, and he called it a Watt balance. He was trying to work on to determine current from mass using something called an ampere balance. And you can see it kind of looks like an equal arm balance here with coils on each side. And that was to be able to tie a really complicated definition of the amp to mass. But it turns out that you can actually use that similar concept to realize mass from the electrical measurements. So an equivalent between an electromagnetic force and a gravitational force, and that's what the Kibble balance really is. And so the redefinition of the SI occurred in 2019, and this is where the SI is really tied to fundamental constants of nature. And the kilogram is defined in terms of H, and so by fixing Planck's constant, we fix the kilogram, but it's also very much related to the Avogadro number. So by fixing either Planck's constant or the Avogadro number, each one is fixed themselves. But in order to do a realization using the Kibble balance, we also need to know very well what the second is. So this goes towards frequency, which we need to know well. And this is the hyperfine transition frequency of a cesium atom, which is used to fix the second. And then we also need to know position or displacement very well, and that is done by fixing the speed of light in vacuum, and that gives us allows us to realize the meter. And then finally, we need to know current very well, and that's linked to the elementary charge of the electron. So we need current or resistance, and that's what we get from this constant. Now, to a lesser extent, we need to know temperature, and so that's now tied in the new SI to Boltzmann constant. And we don't actually have to put in a number for temperature, but we do need to have extremely stable measurements for temperature. And so that really matters to us. And the last of the 7 units, the candela, we don't really worry about too much. I imagine if it would change, it would make it difficult to see the balance, but we won't really worry about that. And we're also tied to gravitational constant to a certain extent, in that we have to know what the local acceleration due to gravity is, and the gravitational constant just scales the impact of mass in the production of an acceleration due to gravity. So I'll build a little bit of I'll build a Kibble balance here so you understand conceptually what it is. And so here we just begin with a simple equal arm balance with a pivot in the middle and then weights on either side, just like this kind of scale of justice or any kind of old time scale. And then we add on one side, we can add a coil that we can run electricity through, a current through, and on that coil we put we call a retroreflector, but it more or less acts like a mirror. And we counterbalance that coil with a little bit of a mass on that side just to keep it equal. And then we measure the position of the coil, which is coupled to the mass pan that we want to measure. We measure the position of that using an interferometer, and I'll describe that a little bit more in detail later. And so we use the interferometer to control the position, to provide feedback to the position of the mass pan during what we call a weighing phase. So what we want to do is put on a mass on the balance, and then we run a current through it to counterbalance the force, the downwards force. We push up with the coil to maintain the position of the mass pan or the coil based on information from the interferometer. And so we measure the current going through the coil in the weighing phase by measuring the voltage drop across the resistor. And so the current going through the coil gives us a relationship between the force due to gravity, so the force on the mass due to gravity, so that's mg is balanced by the upwards force from the current going through the coil. And so as Stuart said, the BL terms, which are related to the characteristics of the magnetic field and the length of the coil, those are very hard to measure. And so what we do is we do a second phase of the experiment where there's a coil on this other side of the balance, and we don't worry about what the weight of that is too much. But we use it to drive, after we take off the mass that we were weighing in the first phase, we take that off, and then we use the current through this side to tilt the Kibble balance, tilt the arm here so that we drive up the coil up through the magnetic field. And by doing that, we generate a voltage across the coil. And so that has to be done at a constant velocity to get the voltage out. And so the voltage that we would measure is equal to the velocity of its movement times BL, which are, again, are the coil characteristics. And then so all we do is we have the two phases of the experiment, the weighing phase where we need to know current, and the moving phase where we need to know the velocity and the voltage. And that combine those together and it gives us something called the Kibble equation. And if we look at these, we can see that mass can be given, in order to get mass, we need to know what the acceleration due to gravity is, g. We need to know velocity very well because we're moving at a constant velocity through the magnetic field. And we need to know current very well, and then we need to measure the voltage, the induced voltage during the moving phase very well. And so as Stuart mentioned, we need to do that very, very accurately. And right now, in order to get voltage, we tie this to the Josephson effect, which is a quantum effect that gives us a very good measurement of voltage. And to give us current, we use what's called the quantum Hall effect, which allows us to measure resistance. And I'll talk a little bit more about that. When all those things are combined, we have mass in terms of a gravity, in terms of gravity, and then frequency. So this comes back to the frequency we saw very early in the presentation, where mass is related to frequency as well as speed of light and Planck's constant. So we have here Planck's constant, and these n's are just integers that come from the quantum effects of the standards. So just to reiterate here, in order to realize a kilogram using a Kibble balance, we need to know these quantities very well. We need to know voltage, resistance, gravity, position, and velocity, and we need to know those to about parts in 10 to the 9, and that's in order to realize it at about this target 10 parts per billion level. But we also need to know pressure, we need to know temperature, we need to worry about magnetic susceptibility, angles, and various other kinds of things. But these are the main quantities that we need to know, and they kind of we need to know them all at the exact same time, because we need to know what's happening at the time of the weighing phase, and we need to know what's happening at the time of the velocity phase, and then those two phases get combined together. So a little description of the Josephson effect. So if we take two superconductors and we put a thin insulating barrier between them, you can you can expose that junction. It's called a Josephson junction, and you can expose that to microwave radiation at a specific frequency, or at a certain frequency. And if this is cold enough down at the cryogenic levels, you get a quantization of states. And so you can look at the relationship between the voltage and current. So current will go through when you shine the microwave radiation on there. This is called the inverse AC Josephson effect. And it will generate a relationship between the current and voltage that's quantized. So you could have various measurements of current in here, but you'll have exactly specific voltage outputs. And so this second step, which is what we operate on for our Kibble balance, or one of the voltages we use for the Kibble balance, is that right here. It's 120 microvolts, but it's quantized, and this H over 2E is actually called the Josephson constant. And so the relationship between the voltage and frequency is scaled by H over 2E, the Josephson constant. And so you can take a whole series of these Josephson junctions, and you can produce, just how you'd put together multiple batteries to get higher voltages. You can make higher voltage measurements using higher voltage levels using multiple Josephson junctions. And so at NRC, we operate a PTB Josephson array, where we can actually select the voltages that we want, and we'll know what those voltages are between 1.2 plus or minus 1.2 volts to a resolution of about 150 microvolts. So that's what we can shift the Josephson levels to. And because we can know what those Josephson levels are to better than parts in 10 to the 9, all we really need to do when we do our measurements is we scale our voltage measurements so that we're always locked to a Josephson level, and then we just measure a small resistance with a small voltage difference with the nanovoltmeter. And so we have a very accurate reference voltage, and then we're just measuring small residual voltages on top of that. And so during the moving phase, for example, we'll always track with a Josephson array and only measure small differential voltages. But as Stuart mentioned, we need to cool this down in a liquid helium dewar to very, very low levels, below 4 Kelvin. Okay, and that operates continuously during the course of our realization experiment. Now, the next thing is resistance. So resistance and current, we'll use those interchangeably here. So this is done by using the quantum Hall effect, which was discovered by Klaus von Klitzing in the 80s, and he won the Nobel Prize for that in 1985. He found that when you take a quantum Hall device, in this case it's I think he was using a silicon semiconductor. We at NRC use a gallium arsenide sample. But if you put that in a magnetic field and cool it down to cryogenic temperatures, then you can get a relationship, a resistance. In this case, it's going to be the current will be moving through the sample one way, and a voltage will be generated transversely on the other side within the magnetic field. And in this case, we can shift the magnetic field, and we can produce a current that is quantized, and we can select a step that we operate on. And so the resistance in this case is related to H over E squared, which is actually called the von Klitzing constant. Okay, so once we have the resistance, we actually don't use the quantum Hall device over the course of the measurement. We have resistors that we measure, and we measure and we calibrate those resistors over time. And they remain in an oil bath, a temperature controlled oil bath, and we never take them out of the oil bath. We take our Josephson system down and we calibrate those resistors in situ. And so the resistors change in time, but what we do is we measure the resistance before and after our experiments. We calibrate those resistors over the time of the measurements. And a typical realization takes about 1 to 2 weeks, depending on the level of uncertainty you want. So the next thing we need to know is gravity. And so gravity, if we just assumed a value for gravity, it varies on the order of about 300 parts per billion over 24 hours. And here you can have a tidal variation seen over 20 days, and that changes in time. And that's affected by the position of the moon, ocean loading, tides, position of Venus, position of Jupiter, all kinds of things. Even the air column above the gravimeter affects what G is. And G is measured conceptually very simply. You can imagine just dropping a ball and measuring how it accelerates. And that's more or less effectively how we do it, except we drop a retroreflector and we use an interferometer to measure its position, and that's all done in vacuum. And so when we do measurements to get gravity, you can see here, this is our gravimeter, absolute gravimeter, which gives us the value for gravity. We measure that on a pad close to the Kibble balance. And then because we actually care about what the gravity is at the mass pan of the Kibble balance, we have to do some corrections. Here we've done corrections based on the masses that we've seen to model how the value that we measure at the on this pad where the gravimeter is to the mass pan of the Kibble balance, and that would be somewhere over here. And so we can do those corrections. We can do it all to about 5 parts per billion, but we measure gravity before and after the experiments and sometimes during the experiment. Now, you've seen that a lot of the things that we have rely on position measurements, and we use a laser interferometer, and that, of course, just uses the interference of a beam of coherent laser beam to measure position. And so it works putting in a laser source, coherent laser source. There's one arm, that light gets split up with this beam splitter, so some of it goes through and some of it gets reflected this way. There's a stationary mirror that reflects the original beam back. And then there's this moving mirror. In our case, this moving mirror is attached to our coil. And so as this moves, what happens, the beam that gets reflected back combines constructively or destructively with the beam coming from the stationary mirror. And the intensity of that light, so you'll have a light fringe or a dark fringe or somewhere in between, that intensity is measured by this detector. And so as you move the coil or the moving mirror, you go through light and dark fringes, and the count or the movement is dependent on the wavelength of the laser. And the wavelength of the laser, again, is traceable to speed of light and time and frequency. And so practically the way we do this is we have our interferometer, which is a transverse Zeeman stabilized Heine laser. And we have this calibrated in situ by our time and frequency group. So we have a bit of a split here with a fiber optic cable that runs to our time and frequency division. So this gets calibrated before and after our realization experiment. It doesn't shift by a lot, but it's enough to be bigger than 10 parts in 10 to the 8 sometimes. And then here's a little bit of the picture of the detectors that we use. I won't describe that too much here. And so the other thing we care about is our thermal control. This has to be very, very precise because the balance itself has the magnet, which is in the Kibble balance, has a fairly big temperature constant, but we have a laboratory that's well temperature controlled, and we can keep the lab constant to less than 5 millikelvin outside the balance for an extended period of time. For weeks at a time, and inside we're at the level of 25 microkelvins for 90 minutes. So a very, very tightly controlled environment. And so this is what the Kibble balance looks like. Here is the magnetic, the magnet. It's a toroidal magnet, and inside is the coil. And then here is the mass pan. And of course, you can see the pivots here, the equal arm with the pivots, which is boron nitride flat. underneath a tungsten carbide knife edge. And here is the coil that we use to drive it during the velocity phases. And this all operates in vacuum. So here it's exposed to air, but we have a lid that goes down and it all runs under vacuum. And vacuum is critical to get to the low uncertainties that you need because it gets rid of buoyancy corrections. It gets rid of changes to the index of refraction. So the interferometry is good. And so here's a little bit of a look at what happens for the mass. We put the mass on and then we measure the current as it's going through, and we measure the drop across the resistor, which gives us a voltage that we measure with the Josephson. And then we take the mass off, and when the mass is off, it's now unstable, so we drive the voltage in the opposite direction. And so everything is balanced so that we're when the mass is on, we're pushing up in one direction, and when the mass is off, we're pushing down in one direction, in the exact opposite and the same magnitude. And it's important because having reciprocal quantities actually eliminates a lot of impacts and uncertainties. And so we can go through that, and this is the velocity phase. We move it up and down, and we move between voltages. That allows us to characterize the coil and the magnetic field. And so the major steps to realize, of course, we calibrate the resistors, the gravity, the laser, and we do a check of the mass for stability. Then we load the mass in the Kibble balance, do our realization measurements, and then we recalibrate everything again, the resistors and so on, and then we aggregate all the data to tell us what the mass value was at the time it was in the balance. So under vacuum at the time of the balance measurement, time of the realization. And so how do we take that from a realization to an actual outside real world? Well, this seems quite complicated, but let me try to guide you through this. First, we start with a set of masses that we put in our comparator. It's our mass comparator. It's got 6 positions. I'll talk about that in a second. We compare that to a bunch of other masses. Then we take the mass that we want to have the realized value of to our Kibble balance. We do the realization, and it tells us what the mass of that is. Then we bring it back to our mass balance to see if it's changed values at all. And then we use that to calibrate traveling artifacts, which then go to the BIPM for this global intercomparison. And that, and that's the first step is the realization. The second step is disseminating that for the global, to shape the global consensus kilogram. And then at the same time, we have one arm goes out to the BIPM, the next arm goes to calibrate the Canadian mass scale. And so for that, we calibrate both platinum standards and we calibrate stainless steel standards. So from stainless steel standards is what we disseminate to the country, and outside NRC. And so briefly, we know that inside mass balance, what we're doing is actually comparing forces. We're comparing forces between the gravitational force that pushes down, and when we're operating in air, there's a buoyancy force that pushes up. And so if you can imagine a mass of a big volume, we'd compare it on the mass pan, we'd measure what value it would give us, and then we would compare it to a mass here, and that gives us a difference between those two masses, but it's only measuring force. And so because there's a buoyancy force that's bigger on a mass of bigger volume, we have to do a correction for the buoyancy, which is this term here. And then we also do a correction for the gravitational force because the centers of masses are different and gravity changes depending on the height. So we have to do a bit of a correction based on the size of the standards. And in our balance, we use, it's called a Mettler-Toledo M1 balance. It's got 6 positions. It's got a load lock so that we can take masses out of the chamber and to our Kibble balance without breaking vacuum inside here. And that allows us to make sure that our masses are stable when they're in the Kibble balance. And we've also measured the gravity around the Kibble balance so that we know what the gravity gradient is inside the balance. We can do those corrections. Now, the one thing that's really important for all of this is how we transfer measurements in vacuum to measurements in air. So what happens when you have a mass in vacuum or in air? There's a layer of, so in air there's layers of waters and there's layers of hydrocarbons on the surface. And when you take the mass into vacuum, that water, those hydrocarbons can come off or they can absorb depending on the environment. And so in order to make ourselves sensitive to those changes, what we do is we take a mass of the same material, the same density, and the same surfaces, but we make a set of high surface area artifacts. And when we do measurements to compare both of those, we can compare them in air, and then we compare them again in vacuum, and more water will come off this one than will come off this one because the surface areas are different. So we can resolve changes of about 1.01 monolayers of water. So if we had just one atomic or molecular layer of water over the surface, we can measure a hundredth of a monolayer difference between air and vacuum on these. So, and then if we wanted to make ourselves sensitive, we could just make even bigger stacks. So we can make ourselves really almost arbitrarily sensitive to the sorption. And that's really good because turns out that if we do measurements in vacuum, we can compare stainless steel to platinum in vacuum or whatever transfer artifact we want without any buoyancy correction. And then we can calibrate stainless steel in vacuum and just transfer that to air using the sorption correction, which we can do to much better accuracy than we could do a buoyancy correction by, say, for example, comparing platinum to stainless steel in air. That's a big correction. And so how well does this work? So for us, we calibrate, this is the phase where we go from our Kibble Balance experiment to the vacuum balance into our primary standards where we store our value of the realization. And this is our historical measurements of our national standard of platinum iridium standard. And so these are our measurements against the IPK before 2014. And then these are measurements after. This is a measurement we did in 2019 and 2021 for realization of our experiment. So we're continuing along the same path. This is how our mass standard changes over time for us, and we track that very carefully. This was our old drift measurements before we cleaned our national standard in 2011. So we can store our realized value into our national prototype. And how do we compare when we send off our traveling standards out to do these international comparisons? Well, 2016, these are all of the numbers. We agree fairly well with the standards of the BIPM and with measurements of internationally. In 2019, we have a bit more of a disagreement with PTB. They found a correction that they've changed in their Avogadro measurements, and so right now, as Stuart said, we're not in great agreement with them, but we're aligned and our numbers are quite consistent and quite consistent with what the IPK values were. And so now, to summarize, the kilogram is now defined in terms of Planck's constant, but in order to realize the kilogram, we need to have a whole bunch of other constants fixed that we can use to realize the value. And so the Kibble balance uses those constants by equating a gravimetric force to an electromechanical force or an electromagnetic force. And that, in fact, takes almost all the primary measurements of an NMI and combines them into a single experiment. And so you really have to know a lot about every aspect of what an NMI does to understand the science, to integrate everything at the same time. And so realization occurs in vacuum, but we need to disseminate that out into the real world in air. And so we have to compensate for the changes that occur between vacuum and air, and we use that doing sorption artifacts. So I just want to thank everybody for your time. Gracias.